Welcome to this discussion on image formation by the eye. My name is Jonathon Lunsford, and I will be presenting today. We live in an incredible world full of amazing technology, especially regarding cameras. Cameras are the closest thing that imitate the human eye. We have cameras that are so powerful they can take pictures of galaxies far, far away, and we have cameras that are small enough to fit into our phone that are still good enough to take high-quality HD pictures. These cameras still cannot compare to the quality of the human eye. The human eye has about 130 million pixels of resolution. That's a lot more than your iPhone's camera. Today we're going to discover some of what makes the human eye so special. Our discussion today will focus on three topics: basic anatomy and physiology of the eye, image formation in the eye, and vision deficiencies. Here we begin our discussion on the general anatomy of the eye. In this picture you can see the iris and the pupil. A lot of people don't know it, but the pupil is just a hole that the light travels through. Right? The iris is the muscle body that controls the size of that hole. So if you're in a dark room, your iris is going to dilate or expand, and that allows more light to travel into your eye so you can see better. If you're in a bright room or a bright space, the iris is going to contract and make that pupil smaller, so less light comes in, and that lowers the intensity so your eye doesn't become damaged. We have here a diagram of the basic components of the eye. And for our discussion, we're going to go in order of things that light passes through. So I'm going to draw a stick figure man here to represent what this eyeball is looking at. Please don't judge my art skills. I'm trying to make him look happy though. He's happy. Okay. And so the first thing light passes through is the cornea. It's the outermost layer of the eye. Just a fun fact, your contact lens is going to sit on the cornea, right about right here. So light passes through the cornea, through the pupil, through the lens, okay, and it's going to travel all the way to the back and hit your retina, okay. So these ciliary fibers that we see attached to the lens, right here and also on the bottom, they're basically muscles that manipulate the lens. This is what allows your eyes to adjust to moving objects, allows you to change what you're looking at from being up close like your phone to something far away like the scoreboard at a baseball game, right? That quick adjustment is possible because of your ciliary fibers, and they change the shape of the lens, right? Light continues to pass through this liquid in the eye called vitreous humor until it makes contact with the retina. The retina is one of the most important parts of the eye. Okay, it's composed entirely of photoreceptors that are stimulated by light. These photoreceptors are called rods and cones, and when they're stimulated, they convert that stimulus into a neural impulse that is then sent through the optic nerve all the way to the brain, and that signal is interpreted by the brain to produce the images that you see. Right? We're going to discuss rods and cones in more detail in the next slide. On the retina, you have two important things. One's called the fovea, and the other is the optic disc. The fovea is the area of highest visual acuity on the retina. It's composed entirely of cones, right? And we'll discuss the fovea a little bit more in the next slide. The optic disc is commonly called the blind spot, right here. It's blind because at the optic disc you have blood vessels entering and leaving, and also that's where the optic nerve is. And since those things are kind of taking up the space of the retina, there are no photoreceptors there, so you can't see any light that strikes that spot. We have here an image that you would be likely to get if you were to visit an optometrist. It's basically a picture of your retina, right? So let me grab my pen, and we have right here your fovea, and we have right here your blind spot, and you can see these nice blood vessels leaving the optic disc, right? And so the retina is composed of rods and cones, as we said before. There are about 125 million rods. Rods are responsible for your vision in low light settings, like night vision, and they do a fantastic job. They do see in lower resolution, and that's why it takes time not only for your eyes to adjust at night, but also for you to make out any details in low light situations. Okay. Peripheral vision is also coming from your rods. A fun fact that I think is really fascinating about your peripheral vision has almost zero color perception. The colors that you can see in your peripheral vision they're actually just being assigned by your brain. Your brain is filling in the blanks because your brain has seen those things before and can make the assumption that the color is still the same. And that way you have some continuity in your vision. Your cones number about 5 to 6.5 million. Cones are responsible for all your color and detailed vision, and they see in high resolution. While they do see in color, one cone cannot make out every single color. They have different wavelengths that they are tuned to interact with, right? And they do best in bright light. And as we said before, they're all concentrated in the fovea. So the fovea is going to be where light focuses the most. Like if I'm focusing on my TV right now, the light that makes that clear and sharp image is striking my fovea. And so that detailed image, whatever you want to have the most detail, wherever you're focusing, that light is going to be striking at your fovea. On this slide, we're going to discuss image formation as well as real and virtual images. To start off, we're going to talk about real and virtual images. Real image, the image is actually brought to focus like at the image position, meaning that the object actually is where it appears to be. Whereas a virtual image, it's actually the opposite. So a good example is a mirror. When you're looking in the mirror, the image you're seeing of yourself, it appears to actually be behind the mirror, right? But that light is not coming from the mirror, it's coming from you. It's a reflection, and that is why it's a virtual image, because the rays of light do not actually come from where the image appears to be. Real images, again, they come from where they seem to be coming from. And so images formed by the eye, they are real images. You know, when I'm looking at my TV, the TV is exactly where it seems to be, right? And so in this example, we have a stop sign. Let's say it's about 30 yards away. The ciliary bodies, they manipulate the lens to allow it to focus that image right on your fovea. If the stop sign were to suddenly change position, an action called accommodation would occur to allow the lens to be manipulated. It would adjust the focal length to help our eyes produce that clear image once again. Okay, with that basic information of image formation in our minds, we are going to discuss vision deficiencies. On this slide, we have diagrams of two common vision deficiencies. The first is myopia, commonly called nearsightedness. Those affected by myopia cannot see clear images at a distance. Like me, for example. This can be corrected by glasses, contacts, or surgery. The second example here, hyperopia, is called farsightedness commonly, and those affected by hyperopia cannot see clear images that are close up. This can also be corrected with glasses. And so we're going to discuss a little bit about why this occurs. And for this slide, we're going to use a red pen. So as you can see in this first image here of myopia, if the lens is too strong, the light rays, they converge before the fovea. The fovea is right here. So what happens when they converge right here before the fovea, that means the image appearing on the fovea is going to be less detailed, right? The strong lens, or also the eye being too long, it just messes with the focal length and changes the clarity of the image, right? In hyperopia, it's a similar principle. The light rays do not converge on the fovea. They theoretically converge behind the fovea. And so that also makes it so you can't see clear images up close, right? And so in a normal eye, I'm going to draw it down here on the hyperopia one. The light rays would come in and converge together at the fovea. Up here, light rays would come in and converge at the fovea. And so these things are commonly fixed today by glasses and surgeries and such. Another common visual deficiency is color blindness, and this is a genetic condition. It's X-linked, meaning the X chromosome is what's going to determine, if you're colorblind or not. This makes it so it's more common in men, since women have two X chromosomes. If one of their chromosomes has the colorblind trait, the other can make up for that deficiency. Whereas in men, we're XY, so if we have a colorblind X, then we are stuck with the colorblindness, right? I fortunately am not colorblind. Colorblindness occurs because there is a lack of or a shortage of cones, or there could even still be cones, but something's wrong with them so they don't function in the retina, right? There's red-green color blindness, which is reduced sensitivity to red and green light because of the lack of cones, once again. There's blue-yellow color blindness, and that's the inability to distinguish blues from greens and yellows from violets. And there's also total color blindness, which is a lot more rare, and it's complete non-function or a complete loss or lack of cones. There's no cure per se for color blindness, but there's a lot of progress and acceleration in gene therapy in monkeys to correct color blindness. So who knows, 10, 20, 30, 50, 100 years from now, there might be a shot that injects a viral gene therapy into your retina that fixes your color blindness. I hope that my presentation has helped you appreciate your eyes even more. In summary, we have learned some basic information about the anatomy of the eye. With this information, we are better able to understand how clear images are formed in the eye. With this basic understanding of the eye's function, we were able to explore why some visual deficiencies occur. Once again, thank you so much for watching, and have a good day.